Hi everyone, I'm Mao Fan from Cornell University. You can also call me Ted, as I mainly go by this English name. This is a joint work with Itai, Dalia, Kartik, and Ling. As you may have already noticed in the title, this talk is about the Byzantine fault-tolerant state machine replication protocol, or in short, BFT state machine replication protocol. So why do we need state machine replication in the first place? To build a decentralized computing service where there's no single service provider that could be fully trusted, we need to replicate the state machine of the given service. For example, to have a decentralized cash payment system like Bitcoin, we know the ledger can't be trusted with any individual participants in the network. Instead, we'll have to let each one of them keep a copy of the ledger to have some fault tolerance. Therefore, the key to supporting such system is to ensure the honest players will still see a local ledger that is replicated and grows consistently with others. Moreover, they have to make sure, even if there are malicious nodes around them, without knowing who, as long as the adversary stays below a certain threshold, the honest majority will have consistent states. Let's have a closer look at the informal definition for BFT state machine replication. As shown on the right-hand side of the slide, the network consists of a number of nodes that have point-to-point, reliable, and authenticated communication channels. This is usually implemented by some PKI infrastructure together with network communication protocols. Among all N nodes, there are at most F nodes that could exhibit arbitrary faulty behavior. This means, as an adversary, I can simply disobey the protocol and collude with other adversaries to try to overthrow the system. Or even worse, I can pretend to be a good person and collaborate until the weakest possible moment to launch an attack. The bottom graph shows the case for 4 nodes, or 4 replicas. The Byzantine replica is in red. Then the state machine replication requires that the execution sequence of the rest honest replicas must always be consistent. This consistency guarantee is usually called safety, whereas liveness means honest replica have to keep executing the sequence, if there's any, without getting into the situation where the algorithm gets stuck forever. That sounds indeed an interesting problem. Unfortunately, it is known to be unsolvable given the well-known FLP impossibility result. To get around the impossibility, people added more assumptions. There are 3 major models. Asynchronous model that weakens the deterministic termination by using probabilistic termination. Partially synchronous model that assumes liveness after network becomes synchronous. And finally, the synchronous model, which assumes an upper bound for the delivery of each message, and this is the focus of this talk. But wait a minute, we've seen so many such protocols. Why do we need another one? In 2008, someone under a pseudonym called Satoshi Nakamoto wrote the Bitcoin white paper. The white paper proposes an incredibly simple algorithm that keeps building a chain of blocks using proof of work. The longest chain is deemed as the canonical chain, which determines the ordering of transactions. To many researchers' surprise, the outcome of such algorithm achieves something very close to BFT state machine replication, although one has to do unnecessary computation to maintain the safety, which is only probabilistic. The beauty of the hashed chain structure has inspired researchers to simplify and even significantly improve BFT consensus. The HotStuff protocol serves as a good example. It summarizes the known quorum-based paradigm in BFT consensus and reduces both the algorithmic and programming complexity. It is the partially synchronous protocol used by Libra project. That leads to our second big question. Why do we need another synchronous protocol that has stronger network assumptions compared to the asynchronous protocol like Honeybadger and partially synchronous protocol like PBFT and HotStuff? Well, it's kind of true that synchronous BFT was not thought to be practical because there has already been fast and more practical counterpart such as partially synchronous protocols. But before reaching such assertion, let's think about why synchronous protocols are not practical. There are 2 main reasons. On the one hand, the execution of synchronous protocols usually relies on the upper bound of network latency. They usually have rounds of operations where all honest participants need to be synchronized for each one of them. Because the latency bound is conservatively chosen, the performance is significantly bottlenecked by the constant wait. On the other hand, the latency bound itself might be impractical. In the real world, although the network latency is mostly well-bounded, there could still be occasional latency spikes. However, this is not the end of the world for synchronous BFT, as it has very unique guarantees that neither the other two models have. It can tolerate more faults and has real-time liveness. For example, if you're in a car with some fault tolerance in its controlling system, you don't want all replicas to struggle to eventually make a decision when a red light or pedestrian is right in front of you. Interestingly, such embedded use case for fault tolerance could make the latency bound assumption, delta, practical, as the circuitry could support highly reliable links with bounded latency. Moreover, malfunctioning chips could emit random signals as outputs even if they are not hacked, and thus visiting faults exactly capture the property. However, for a more popular use case such as blockchains nowadays, the performance issue caused by lockstep execution of synchronous protocols is less ideal, and the delta assumption may not always hold. This inspires us to borrow something good from those asynchronous and partially synchronous protocols. Could we remove the round-based synchronization as much as possible to even allow some asynchrony in the synchronous model? Or even better, could we optimistically switch to a communication pattern that is very close to partially synchronous protocols like HotStuff or PBFT? It's a common practice in engineering to make the common case as fast as possible because the common case is most frequently used and usually tends to be simple. Finally, could we even weaken the conventional synchronous model to make it more realistic? Well, the answer to all of them is yes. Our Sync HotStuff protocol is largely inspired by chain-style BFT consensus protocols. It uses quorum certificates and a similar philosophy of locking mechanism as in HotStuff. It is also leader-based, which means it has a long-standing leader for the steady state of operations. The basic version of Sync HotStuff assumes standard synchronous model. However, unlike many other synchronous protocols, it is not a lockstep protocol, so that the execution of replicated blocks are scheduled with some asynchrony. As for latency, it achieves 2 capital delta of its latency, the best of its kind. Moreover, the protocol can be incrementally and easily extended to be even more realistic. In our paper, we make very few changes to the original one to support a weaker than synchronous model. The sluggish mobile model allows at most dishonest replicas to violate the capital delta bound at any given time, and such dishonest replicas can be mobile. This model captures a more realistic network scenario where there could be occasional latency spikes, although the overall latency is still bounded. Finally, we introduce optimistic responsiveness to the protocol to even get rid of the capital delta limitation so that the system can move as fast as network propagates, given that votes from 3/4 of all nodes arrive in time and the leader is honest. We also evaluated the basic Sync HotStuff protocol in comparison to the other famous synchronous protocol, Dfinity, in an apple-to-apple comparison. Moreover, to show Sync HotStuff is realistic, we also compare it with HotStuff, partially synchronous protocol. Overall, it exhibits very similar throughput to HotStuff as we expected, thanks to the lockstep-free design of Sync HotStuff, and significantly outperforms Dfinity protocol in both throughput and latency. We can read our paper for more details in this part. So for the remaining minutes, I'll briefly walk you through the basic Sync HotStuff protocol to explain how it works and why it makes sense. Let's first take a look at the main data structure, the chain of blocks in Sync HotStuff. Like standard blockchains such as Bitcoin, we use a tree of blocks where each block contains a parent hash to its parent block. The payload of each block is the command or operation for the state machine to be replicated. Since the consensus protocol does not rely on its content, but just provides a consistent ordering, we just use CMD to represent it. Apart from blocks, the other mostly used concept throughout our protocol is quorum certificate, or QC. A QC is essentially a proof of the existence of F+1 votes for a given block in a certain view. It could be implemented by some fancy threshold signature scheme or just by putting together a set of signatures, where each one of them certifies one among F+1 votes. The key observation for a QC is that among all votes, there must be at least one vote from an honest replica, because they are F+1 votes. Moreover, it is also the best effort after a voting process to demonstrate the result, because given F adversaries that could simply refuse to respond, one can only hope for F+1 votes within delta time. A certified block is a block that has got F+1 votes collected locally into a QC. For example, in this diagram, block BK gets majority votes, and thus there is a QC that is kept locally by a replica to certify the BK. Unlike HotStuff, in HotStuff, QCs are not contained in the blocks, but stored in a separate pool which updates itself by trying to construct the new QC once more votes are received. Now it is time for our steady-state protocol, the common case. Normally, when the leader is honest and the system keeps making progress, new blocks are repeatedly proposed by the leader. In leader's proposal, it contains the QC of some previous block and the content of a new block. This means in steady state, the leader needs to wait for the votes to previously proposed block before it generates the next one, and thus it takes exactly one round-trip time between the generation of two adjacent blocks. The commit of a block, noticeably, does not interfere with the progression of block generation. For example, in this diagram, for a replica that first gets the proposal and sees block B3, it votes for B3 and starts its commit timer immediately. B3 is committed when the timer goes off after 2 delta time. This concurrent timer is the key to our fast steady-state protocol, because it allows the leader to move on to the next step before the previous block gets finalized. Therefore, when the network speed is actually fast, there might be a pipeline of block commit events timed and scheduled, while the throughput will be the same rate of block generation. Let's take a more detailed look at the network communication pattern that goes under steady-state operations. In this diagram, horizontal lines shows the timeline for each replica, including the leader A. First, A consumes a command from the client, wraps it up into a new block, and broadcasts the proposal to all replicas, including itself. For each replica getting the proposal, it first votes for the block if there is no conflicting block that has already been voted. A conflicting block means a block that diverges from the path of the current block. An honest leader does not generate such blocks. Once F+1 votes are received, A can collect a QC for the certified block B1, and then put the QC as part of the next proposal for B2. From the diagram, we can clearly see the reason for having 2 capital delta as the commit timer. If A is malicious, it could generate conflicting blocks and equivocate to break the safety by selectively sending out the different blocks. To counter this, an honest replica always needs to forward the message if it originates from some single source. So whenever an honest replica receives a proposal, it also forwards it as part of the vote. In doing so, all honest replicas could just detect such equivocation with 2 delta time. Although our proofs for safety and liveness do not rely on discussing all possible attacks that could be made by adversaries, there are still 2 major ways for the Byzantine players. Interestingly, both are explicitly detected by our protocol and trigger a view change. Either there are conflicting blocks showing that the leader tries to equivocate to attack safety, or it stays quiet all the time trying to break liveness. Due to the limited time, I will only skim through the next few slides about the rest part of the view change and its proof. Since this is a video, you can feel free to pause at any time to check out your most interested part. The key part to start a view change is to ensure all honest replicas are well synchronized when they quit their current view. Here we ensure that the time difference between the earliest and the latest one is at most delta. After an honest replica quits a view, it also does some extra steps to make sure the committed blocks are always preserved from one view to another, even if there are some Byzantine replicas in the system. After that, the entire view change is complete. There are two important lemmas to prove the safety of the entire protocol. The first lemma ensures no conflicting blocks are committed within the same view, and the QC of the highest certified block captures such commitment. Then, in our second lemma, we show the QC of the highest certified block is passed on across different views. Finally, with both lemma in place, it's fairly straightforward to show the safety guarantee. The liveness should also be easily reasoned about due to the timed block commit and strongly synchronized view change operations. Thanks for watching.